Hello everyone. We're entering an exceptional period where all have to fight to slow down the spread of COVID-19. We don't know how long it'll last, but we'll all do our best to help. So at EPFL, all courses are going online. Here is how we will proceed. We will use online interactive lectures with Zoom for most of the sessions. There's an exception for the first 2 hours of this Monday morning, where the courses are pre-recorded. We hope you will enjoy our courses. So this is the advanced communication part of the Smart Grid Technology course. Last week, we studied how TCP-IP is used in the context of smart grid communication with focus on traffic control and network accuracy. Today, we will discuss time synchronization. You have seen with Mario how time synchronization is used to measure phasors. What we will discuss today is how we can use the network rather than a direct GPS antenna to carry the synchronization information. Network time synchronization is used in everyday's life. Your computer, this computer, your smartphone probably uses a protocol called NTP, the Network Time Protocol, to synchronize the clock of the device with universal time. Why do we need to synchronize clocks? Well, because they're not perfect. So clocks are based on crystals that oscillate at a nominal frequency, but they're not all perfect, and they deviate with an accuracy which is quantified with various measures. You have seen some of them, the Allen variance, for example, but at a very superficial and simple level, we can say that the relative accuracy of a clock is the difference between the number of ticks of the clock over a long period of time relative to the number it should have done if it had been a perfect clock. For example, a clock that is at 1 gigahertz will tick 1 billion times during 1 second. If its accuracy is 10 to the minus 4, that means it will do 1 billion ticks, plus or minus a difference that, roughly speaking, should be between 10 to the minus 4 times a million, plus or minus. 10 to the minus 4 is expressed in ppm, gives 100. ppm is part per million, so 1 ppm is 10 to the minus 6 relative accuracy. Cheap crystals that are used in low-end devices in industrial networks have an accuracy of 10 to the minus 4. Better crystals are used in watches. They have an accuracy of about 20 ppm. And if you need very, very accurate timings, you can go way, way below, like with rubidium oscillators. If your clock is not perfect, and all clocks are not perfect, what happens? Well, over time, it will drift. For example, your ordinary watch, if you don't synchronize it with NTP, will vary by 1 or 2 seconds per day. So 1 or 2 seconds per day, 173 seconds, that's 20 ppm of 1 day, right? So after a number of days, your clock will be completely off. Time synchronization is the process by which you put the clock back to the correct time. When you do this over a network with protocols like NTP, Network Time Protocol, or PTP, Precision Time Protocol, you almost do the following things. You have a clock A and a clock B, and here I'm showing the 2 clocks at the same time. Of course, this is a view of mind. Nobody can see the 2 clocks are exactly the same time, except if they are in the same location. We see that clock B is 16 time units ahead of clock A. That's the offset difference that I mentioned before. The goal of this protocol is to compute this 16 and make sure that B will get back to the same offset as A. So here, A is the master clock and B is the slave clock. How does it work? Once in a while, for example, here at time 20, A sends a message to B saying, here is my time. My time is 20. The event one is when B receives this message. So B receives it here at time 66. If there would be zero propagation and transmission time between A and B, then B would know the offset. It would know there is an offset of 46. But this is not correct because there is a delay that is also unknown to A and B. That's the problem. So B knows there is a difference, but B doesn't know what is the time that this message took. So the next thing that B will do is measure the time. In order to measure the time, B will do a round-trip time measurement. What B really needs is not the round-trip time measurement, it's the time from A to B. But what B will do is measure the round-trip time. B will send a message to A will echo it back to B, and the time from sending to receiving is the round-trip time. Is the round-trip time? Well, quite not exactly, because of course we cannot assume that A takes zero time to receive the message, parse it, realize it's a delay request message, and send it back immediately. So this delay, of course, is polluting the measurement of the round-trip time if it's not correctly accounted for. So what A will do, it will estimate the time spent between receiving this message and sending the reply, the delay response here. The estimation will be done by software for systems like NTP with an accuracy of order of millisecond. It will be done in hardware for things like PTP with an accuracy which will be much better, a fraction of a microsecond. When B receives this message, this is event 2, it knows the time that was taken by the message, 156 minus 86. It's received at 156, it was sent at 86. B knows also the time that A took responding to this message. B subtracts this quantity and obtains a round-trip measurement of 60. But B needs the one-way delay. So B will make the assumption that the delay in both directions are the same, which makes sense. If there is a bidirectional cable, then the signal propagates at the same speed in both directions. If transmission rate is the same in both directions, then also the time to send the message is the same. Therefore, under those assumptions, that makes sense. So B will divide the quantity for the round-trip time 60 by 2 and obtain 30. So at this time, B has an estimate of the time taken here. B remembers this message. So there was a difference from 66 to 20, a difference of 46, minus the one-way delay, estimated to 30. Therefore, the offset seen by B is 16. So B will change its clock. At time 176, it will get it backwards by 16 time units. And at event 3, the time at B becomes 160. In this case, we see that the two clocks are synchronized. Of course, we don't do things exactly in this way. There is a little problem here. What is the problem? Well, if you measure things in system B, you see that the clock goes backwards in time, which would be very embarrassing. You could have negative measurements for times, which is physically impossible. So this will not be done in such an abrupt way. In fact, if there is a sudden change like this, then B will implement this change very smoothly over time, such that the corrected time still remains increasing. This is, in theory, the calculations that are done in the example that I presented before. So you have simply the same as before, but with formal explanations. We saw that B was a bit lazy and estimated the one-way delay by measuring the round-trip time and dividing by 2. Couldn't we be smarter? How could we do a bit better? Here's a question to you. Make a pause, think about it, and resume to see the answer. Here is the answer. Well, embarrassingly, it is impossible. It is impossible. It is not possible with a system like NTP, PTP, or any network time protocol to measure one-way delays. Why is that? Well, let me explain here two scenarios. Here I'm showing the same as before. There is an A and a B system, and I have a network time protocol, which is consisting in events that are sent from A to B, messages that are sent from A to B, and the events are sending or receiving a message, and these events occur at some times. And anything that the time stamping protocol will do is associate the events with the measurements of time done in the local clock. So here, A sends a message at a time which is event 0, measured with the time of A, TA of 0. It's received at B, and the time measured by B will be the time at which it was sent, plus the one-way delay, which is D, plus the offset, because the clock of B is offset by omega. Here I'm assuming the offset of B is constant during this period of time. Then B responds at a time TB of 2, and the message is received by A at a time TA of 2, which is the time it was sent plus the one-way delay, minus the offset, because the offset of A with respect to B is minus omega. So whatever you do, any time synchronization protocol will do computations like this one. Now look on the right at the same scenario with a difference. The offset here is different. It's modified by a quantity epsilon, positive or negative. I subtract epsilon. And I add the same epsilon to the one-way delay from A to B. And I subtract epsilon to the one-way delay from B to A. I'm assuming the one-way delay in both directions are not the same. If they are the same, there's no issue. I would just compute the round trip time and divide by 2. But the issue is what happens if they are not the same? Can we measure it? Here, if we do the calculations, we see that this minus epsilon here and this plus epsilon here compensate in both cases. So if you look carefully at the timings here, you see that the values are the same exactly everywhere. So those two scenarios produce exactly the same timestamps. But they are different. In one case, the offset is omega and the delay dd prime. In the other case, the offset is omega minus epsilon and the delay d plus epsilon d prime minus epsilon. What does this mean? It means that it is impossible to make the difference between those two scenarios for a network time protocol, because the only thing that such a protocol will see are the timestamps related to the events. We see that it's impossible because there's a confusion between the offset and a difference in the delays. If the delays are asymmetric, then the asymmetry can be confused by a difference in offset. So the morality is that it's impossible. I showed a very simple case with only two devices, A and B. Now we could ask, what if we are smarter and we have a network, we have a number of devices, not two, but n devices that are trying to keep track of the offsets that they have with respect to each other. They're trying to synchronize to each other. In order to synchronize, they need to measure their one-way delays, but there is a general result that we will not see in detail, but that generalizes what I just explained now. If you have a general network with n nodes and L unidirectional links, the number of delays that can be measured by any timestamping protocol is upper bounded by this quantity, L minus n plus 1. So this quantity is, of course, strictly less than n, L. So it is not possible to measure all unidirectional link delays. If we take the example of before, we had n equal 2 and 2 links, because we have 2 directions for the link. So L is equal to 2. We see that we can measure at most 1 delay. So If we know by an oracle what's the delay in one direction, then we can measure it. Or we can measure the round-trip delay, which is the sum of two delays, but we never have enough degrees of freedom to measure everything. So that's a problem. That's a problem for NTP and PTP because links are not always symmetric. Links are not symmetric, for example, because the communication technology might not be using the same coding scheme in both directions, so that messages of a smaller, the bit rates might be different in two directions. Or more subtle things, if we use optical carriers, optical fiber to transmit the signals, the wavelength might be different or typically different, and propagation times in the glass or plastic is different for different wavelengths. So there may be differences in propagation time. Those differences are minuscule, but we are trying to catch differences that are less than a microsecond, so they do matter. So you need to account for this. In NTP or in PTP, you will account for the asymmetry because you know, in some sense, the asymmetry. If you know one fiber has a propagation time which is some epsilon larger than in the reverse direction, then you make the assumption that you know exactly what is the ratio between the two delays. Therefore, you can gain with this 1 degree of freedom and still measure things. So if the asymmetry is due to things that you know and that you can quantify, then you can measure one-way delay. If the asymmetry is not known, and this is, for example, because there is an attack, if you can introduce a delay between two nodes that is different in the two directions, then all the timestamping protocol will be full. So this is an attack against time synchronization. This was about time synchronization, which is about putting the clock back to the correct time. There's another concept that's important, the clock drift. The drift is what we call the difference in speed, the accuracy in ppm. The larger the drift, the more we need to do corrections and the less accurate the time will be, because of course between two corrections the time is a bit inaccurate. So it's possible to improve the accuracy of a timestamping protocol by trying to learn what is the rate of one clock with respect to the other. Imagine, for example, that whenever B receives a message from A, it's always off by 1 microsecond. And A sends this message every second. Then B learns that its clock is a bit slower. It loses 1 microsecond per second, so it loses 10 to the minus 6. So B can have an estimate of its drift, and its i.e. difference in rate. So B could adapt to that. Having estimated this, B can correct the times that are displayed by the clock by saying, oh, I know my clock is 1 ppm too slow, so I subtract a fraction 10 to the minus 6 of any elapsed time interval that is being measured. So that's one way that can be done. In general, this process is called synchronization. So synchronization is any mechanism that is used to adjust the rate of the clock based on messages we receive from another clock, typically. Synchronization will make the system more accurate, will make the adjustments that we do with timestamping smaller, and therefore improve the global accuracy. Synchronizations can be done from the timestamping protocol themselves. They can be done from other mechanisms that are even more accurate. Ethernet is typically asynchronous. Asynchronous means that when an Ethernet system sends a packet to another Ethernet system, the clock of the source need not be synchronized with the clock of the destination. Why do we need synchronization when we send Ethernet packet? We've seen that we need synchronization to measure PMUs, but synchronization is also a fundamental problem in digital communication. Think about it. When A sends a message to B, The message is sent as a sequence of bits. Now, what are the bits in reality on the line? Well, there are waves. There are, for example, you send a sine wave, which you modulate by reverting the sign, for example, by multiplying by +1 or -1. So you send a signal that is received by sampling it. So you sample the signal, but now if you sample with the clock that is not synchronized, if you send, for example, 1 million bits, which is 1 megabit, which is even less in megabytes, so that is something that is done very quickly in a fraction of a second. When you read this signal on the receiving side with a non-synchronized clock, then after reading 1 million transitions, so 1 million peaks of your sine wave, if your clock has an accuracy of 1 ppm, then you're off by one period of your sine wave. So of course it will not work. Your clock will be wrong. You will not be able to read the signal. So synchronization is needed in any communication system. Some communication systems synchronize all clocks. This is typically what the cellular telephony networks do. They synchronize all the clocks with GPS kind of accuracy to avoid this problem. Ethernet systems that we use every day with our computers or Wi-Fi do not do this. They do not synchronize the clock. How can they manage to read streams of bits that are received? Well, by using a system called phase lock loop and a synchronization per message. When an Ethernet system sends one packet, it starts by sending a preamble, a sequence of 8 to 10 bytes, or up to 100 bits that are useless. They carry no information, but they are just used to send enough peaks of the signal so that on the receiving end, there is a circuit that will lock itself to the phase of what is received, and therefore will detect the peaks of this signal. By detecting the peaks of this signal, it can adjust its local clock immediately and then read the rest of the message. Of course, this accuracy is not perfect, so you do that for a few thousands or tens of thousands of bits, and then when a new packet comes, you resynchronize again. So Ethernet is non-synchronized, which means simply that it is resynchronized at every packet. But the clock that is used for reading a message is not the clock of the receiving device. It is a clock that is derived from the signal. Well, we can go one step beyond and do what is called synchronous Ethernet. The idea of synchronous Ethernet is we do that all the time. With synchronous Ethernet, the devices always send some signals on the line and always try to synchronize to the received signal. In other words, to do synchronization. This type of synchronization is not a time synchronization. We just capture the rate at which there are transitions in the signal. In other words, we can lock the frequency. So if you do this, you will greatly improve the accuracy of PTP, and this is what PTP v3 is doing. It adds synchronous Ethernet rather than the standard Ethernet and achieves an accuracy which is well below the microsecond. Voila, that's the story of clock and accuracy. Now, when we discussed of all those things, when I discussed timestamping, I ignored the clock drift. I assume the only problem is an offset. Clock B has an offset of omega. There is a one-way delay D. In order to estimate omega, I need D, and that's what we discussed before. But in reality, the clock of B is not perfect. It's also drifting. What should we do if we don't do synchronization? How should we account for the drift? Think about it, do a pause, and start again to see the answer. Well, the answer is yes, of course, we could do synchronization. Synchronization would mean that between A and B, there is a synchronous signal that is sent and that is constantly used by B to see how fast the signal sent by A has transitions. Radio propagation systems are linear time invariant channels, so the frequency is kept unchanged. So whatever is sent by A is received by B at the same frequency. So that's would be one way to solve the problem. But another possible answer is, after all, we don't care. We don't care because when we measure intervals of time that are short, then the error we do on the measurement is given by the ppm. So if I measure an interval of 10 milliseconds with a clock that is an accuracy of 1 ppm or 2 ppm, for example, then I have an accuracy of 0.2 nanosecond, which is negligible, is below any accuracy that we could have to acquire the signals anyhow. So when we measure short intervals, it doesn't matter. The accuracy of the clocks are good enough for everything we're doing. Of course, this doesn't mean that we don't need to do something with synchronization. The problem being that clocks keep running over time, and over time they accumulate an offset, which itself needs to be compensated. Voila, we have seen the essential theory part. How does it work in practice if we use a time synchronization protocol device? So PTP uses UDP over IPv4 or IPv6. There is also a version of TCP that works directly over Ethernet without IP. Here we find an example of what we discussed last week, is that in industrial networking, we have applications that run directly over the MAC layer, so that exists also. If you want to use PTP, you need special routers and bridges. Most of the time it's just for bridges that have hardware assistance for timing messages. Why do we need hardware assistance? Well, we need to know exactly when a message is sent. Remember, the sync message needs to be timestamped with the time it is sent. Protocols like NTP do that in software. So my computer does it in software. It asks the clock, what time is it, puts the timestamp and sends it in the message. But of course, this time measurement is inaccurate when you do it in software, because you ask for time, then a number of things happen. Your operating system is not doing it instantly. It may take some time to respond to it. And this time is variable because it's a multitasking system. So if you want accuracy, you do it in hardware. That's one thing. Second, there may be also intermediate devices. For example, if you want to synchronize A with B, but A and B are connected through an Ethernet switch, then the time taken by packets to cross an Ethernet switch is variable. Remember, a switch, which is a MAC layer intermediate system, like a router, which is an IP layer intermediate system, a switch is a queuing system. So a queuing system has a queue, and how much time a packet takes depends on what's in the queue. Now, of course, you could say, let's give higher priority to the PTP messages, which is typically what is done. But even then, you cannot guarantee that there are not several PTP messages that would be competing. So the trick that is used is to require that the switches, if they support PTP, they would time everything. They would measure accurately the time spent by a message through the system. Let's examine here an example. A sends this time sync message, it timestamps it and say it's at time TA. This message goes via an intermediate system. This intermediate system will record how much time it spent in the system, here 3.46 milliseconds. Then B receives this message. It will see not only time it would send, but also the time spent in the message. Then we saw that B will also trigger a round trip measurement that will consist in a delay request followed by a delay response. Both the delay request and the delay response will also spend some time in the intermediate system X, but this time will be recorded here. So when B receives this, it can timestamp, compute the difference, remove the time spent at A and the time spent in all intermediate systems on the way, and therefore get a very accurate measurement. So this, of course, requires that your PTP switches or PTP routers have hardware assistance for timing. Voila, that's all for the part on PTP. Our next topic will be MPLS. But before that, let's do a break.